Hi Dr. Mark and all the audience. My name is Aaron Lau, and today I'll be presenting my computer system research report. In this presentation, I'll be walking through three major areas covered in the report. First, I'm explaining the key difference between microprocessor and microcontroller, including how they are designed and what they are used for. After that, I move on to the how program written in high-level language and translate into instruction to the CPU and actually understand. And finally, I'm presenting two practical implementation, a basic calculator and traffic light control system, which is a research challenge. It's built in both Python and assembly. This example helps highlight how two language difference in terms of complexity, control, and performance. I go through each section step by step following the overall structure of the report. In the first part of the presentation, I start by looking what exactly a microprocessor is. A microprocessor or MPU acts as a main computing engine of a system. It built to carry out operations such as arithmetic, logic, processing, and overall system control. One important point is that a microprocessor does not include built-in memory or input-output hardware. Instead, it relies on external RAM, storage, and support chip. This design allows it to achieve very high performance and make it suitable for running full operation system in Windows, Linux, or Mac OS. Next, the report explains how a microprocessor is built internally. A microprocessor contains several core hardware components that work together to execute instruction, manage data, and coordinate all operations inside the CPU as the image shown. The core components include: first is arithmetic logic unit, or ALU, which is responsible for arithmetic operations like addition and subtraction, as well as logic, operations such as AND, OR, and comparison. Next is control unit, which manages the entire instruction cycle. It handles the fetch, decode, and execute stage and ensure every part of the processor receives the correct control signal. The processor also includes register, which act as extreme fast temporary storage. This whole operand's memory address the program counter, stack pointer, and intermediate result need during program execution. Then we have cached memory system, which typically include L1, L2, and something L3 caches. As the picture shown, L1 is the smallest and faster, L2 is the larger but slightly slower, and L3 is the biggest and shared across the core. These caches reduce memory latency and improve performance. Another important component is bus interface unit, which manages communication between CPU and external components through the address, data, and control bus. And finally, the memory management unit, or MMU, showing in the diagram, is responsible for translating visual address into physical address. It also handles memory protection and isolation, allow modern operation systems to run multiple processes safely. These components work together to make modern microprocessors fast, efficient, and capable of running complex operating systems. Modern microprocessors also rely on several architecture techniques to boost their performance. These include pipeline caching, parallel execution, superscalar design, and out-of-order execution. All of these work together to reduce delay and allow processors to execute more instructions in less time. In the architecture section of my report, I highlight three important architecture models. The first is von Neumann architecture. In this model, both program instruction and data share the same memory and bus system. This design is a simple and wide use, but it can create a bottleneck because instruction and data complete for the same pathway. The second is pipeline architecture. Pipeline divide instruction execution into multiple stages, which allows several instructions to overlap as they move through the pipeline. This means while one instruction is being executed, another can be decoded and another can be fetched, significant increase throughput. The third model is superscalar and out-of-order execution. In this approach, the processor can issue and execute multiple instructions per clock cycle. Out-of-order execution let independent instructions run early even if previous instructions are still waiting for data. This keeps the processor busy and reduces waste cycle. This architecture design enables modern MPU to run advanced operating systems smoothly, support heavy multitasking, and achieve high overall efficiency. Next, include several commercial examples of modern microprocessor, and the picture in the report help illustrate them clearly. The first picture shows the Intel Core Ultra 9 285K. This flagship desktop class processor based on the Intel hybrid architecture. It combines 24 core 8 performance core and 16 efficient core with 32 threads. It also includes a large 36 MB caches and can boost up to 5.7 GHz. What stands out is integrate AI acceleration, which make this processor suitable not only traditional workload like gaming, content creation, but also for AI-driven tasks such as on-device machine learning inference. The second image show is AMD Ryzen 9 9950 X3D. These processors use AM Gen 5 architecture and feature 16 core and 32 threads. Its most notable feature like AMD 3D V-caches technology, where an extra layer of L3 caches is stacked on the top of the CPU. This significantly boosts the performance in gaming multi-threads workloads by reducing memory latency. The third example is the Apple M4 chip. This is an ARM-based system on chip used in the latest Apple device. It combines high-performance CPU core, efficient core, a powerful GPU, and neural engine capable of 10 trillion operations per second. Apple target a balance between sustainable performance and energy efficient. The fourth image shows a Qualcomm Snapdragon 8 Elite Gen 5. The chip is designed for flagship smartphone and mobile device. It integrates next generation Crypto CPU core, advanced 5G connection, and strong AI acceleration for photograph, gaming, and XR application. Together, these examples demonstrate that microprocessors are used across a very wide range of devices, from high-end desktop PC all the way smartphone and tablet, depending on their architecture and performance level. The next section of my report shift focus from microprocessor to microcontroller. A microcontroller is complex self-contained integrated circuit that include a processor, core, memory, and peripherals interface all on one chip. Unlike the MPU, which rely on external RAM and peripheral controller, MCU integrate flash memory, SRAM, timer, GPIO pin, analog interface, and communication modulars internally. Because everything is built in one single chip, microcontrollers are much better suitable for real-time tasks and embedded applications such as appliance, automotive control module, industry controller, robotic, and IoT device. Their design emphasizes low power consumption, reliability, and ability to interact directly with sensor and actuator. Next, I explain the internal components that make up the MCU. First, for the CPU core, most MCUs use lightweight RISC-based cores such as ARM, Cortex-M, AVR, or PIC. These are optimized for predictable execution and low interrupt latency. Second, for on-chip memory, MCU contain multiple memory types, which is flash or ROM, which store the firmware, EEPROM, used for configuration data that must be retrained, SRAM, which store the variable and the stack during runtime. Because the memory is on the same chip as the CPU, access is fast and predictable. For the third, digital and analog peripheral, unlike the MCU integrates variety of models such as GPIO pin, timer, PWM controller, analog, digital converter, digital to analog converter, and communication interface. This subsystem allow direct control of external hardware without needing additional chips. Next is clock system. MCU including internal oscillator, watchdog timer, and PLL-based timing system that ensure stable and precise operation. For number 5 is low modes Many MCU support deep sleep or ultra-low power state, making the ideal battery-powered device such as wearable or remote sensor. Because all of these components are integrated into one device, MCU can operate without any external hardware other than a power supply. In the architecture discussion, I highlight that many microcontrollers use Harvard architecture. This architecture separates the instruction memory and data memory into two different buses. The advantage is that the CPU can fetch the next instruction while simultaneously accessing data, which improve execution speed and ensure predictable timing, something that is very important in real-time embedded system. My report also includes several examples of popular microcontroller. First is PIC18F57Q43. As the image shows, it is an 8-bit MCU commonly used in the industry application because of its low cost and flexible input and output option. Next picture shown is ESP32S3, a power MCU with Wi-Fi, Bluetooth 5.0 and support for AI acceleration, making it very popular in IoT, smart home application. For the third one is MSP430FR6989, a 16-bit MCU now extremely low power consumption, used in medical device metering system, long life battery production. Last is Raspberry Pi RP2040, a dual-core ARM Cortex-M0 Plus microcontroller that uses high flexible use in education, hobby electronic, and robotic. This example shows how diverse MCU application can be, from simple application to AI-enabled edge device. In this section of the report, I compare microcontroller and microprocessor using the table shown. Overall, both MCU and MPU are central processing devices, but they optimize for different roles. MCU focus on controlling timing and efficiency, while MPU focus on high computational performance and multitasking. Let me walk through each feature in the table. For integration, MCU integrate almost everything on the chip: the CPU, flash ROMs, SRAM, timer, ADC, DAC, GPIO pin, and serial interface. This high level of integration make them compatible, reliable, and suitable for embedded system. MPU, on the other hand, include on the CPU. They rely on external RAM, external flash storage, and external peripherals controller. This make them more flexibility and powerful, but also more complex in terms of system design. MCU typically use the Hubbard architecture, where instruction and data travel on separate buses. This separation helps maintain predictable timing, which is important in real-time control tasks. MPU usually use the von Neumann architecture, which a shared memory bus that also often include a deep pipeline, superscalar execution, and out-of-the-order processing of maximized performance. For the instruction set, most MCU use lightweight RISC-based instruction set like ARM Cortex-M, AVR, or PIC. These are simple, fast decode, and designed for low latency. MPU typically use high-performance RSIC, CSIC architecture such as ARM Cortex-A, X36. This instruction set support complex operation system and high-level applications. So for the clock speed, MCU operate in the 10 to 100 MHz, which is sufficient for sensor reading, motor control, and IoT tasks. MPU operate in a gigahertz range, allowing them execute billions of instructions per second and heavy workload. Then memory, MCU include one on-chip flash and SRAM, but the capacity is limited and fixed. MPU is external DDR memory combined with multi-level cache like L1, L2, and L3. This provides much higher memory bandwidth and scalability. Next is power consumption. MCU are extreme power efficient, often operating in microwatts or milliwatts. They support deep sleep mode and are perfect battery power or always on device. NPU consume far more power, typical from 10 watts up to 150 watt more, and require active cooling. For real-time capability, MCU are built for determined timing, meaning their response are predictable. This is crucial for the real-time system such as automotive controller, industry automation. MPU are not inherited real-time because the pipeline caches and multitasking. They can usually for real-time application only specify operating system or tuning. And then the operating system, MCU usually run bare metal firmware or lightweight RTOS, like free RTOS or JetBrush. NPU can run full-scale operating systems such as Linux, Windows, Mac OS, or Androids. For the next application, MCU appear in IoT sensor, motor driver, robotic, wearable smart home device, and automotive ECU. They excel in control sensing and low power application. MPU are used in PC, server, smartphone, gaming, console, and edge AI system, and any environment requiring high computational power. And last is the major vendor, common MCU vendor including Microchip, NXP, STM, TI, and Aspersive. MPU vendor include Intel, AMD, Apple, Qualcomm, and ARM. So summary, MCU are optimized for control, low power consumption, and real-time application, while MPU are optimized for computing power, multitasking, and running advanced operation system. Now I move to part 2 to explain how a program written a high-level language is translated into the CPU can actually run, and diagram illustrate the process. We start with the source code, which is the human-readable program written in language like C, C++, or Raj. The CPU cannot execute this direct, so it must go through the several transaction steps. The first stage is preprocessor, which prepare the code. It expand micros, include header file, and clean out the program before actual completion. Next is compiler. The compiler analyze the source code, perform optimizations, and convert it into assembly language that match the instruction set of the target processor. That assembly output is needed passed to the assembler, which translate the instruction into machine-specified object file, essential binary instruction the CPU understand. The linker then combine all the object file together along with any external library to form one complex executable file. When the program is launched, the loader load the executable into memory, set up the stack and data section, and prepare the CPU to start running it. Finally, the program enters CPU execution, where the processor performs its fetch, decode, execute cycle. The CPU fetch each instruction from memory, decode what operator is present, and execute it using register, the ALU, and other internal component. For interpreter language, the process is a bit different. Instead of production standalone executable, the code is translated into bit code and execute step by step by interpreter. Even though the transaction flow is different, both compile and interpret language ultimate convert human readable instruction into a form the CPU can process. This entire pipeline ensures that high-level program can run efficient on real hardware. Next, I will move to the machine language, which the first one is first generation language. In this section, I continue by explaining the evolution of the programming language. This very first generation language is machine language. This is the most basic level of programming, where instructions are writing directly in binary, just 0 and 1. These are the exact pattern that the CPU understand native. It run extremely fast because there are not transaction required. But it almost impossible for human to write large program this way. One small mistake in a long string of bits can break the entire program. So while it offers total hardware control, it is not practical for most developers. The second generation assembly language is a small step above machine code instead of binary number. Programmers use short mnemonic like MOV, ADD or JMP, which represent CPU instruction in the more readable form. Assembly is still very close to the hardware, meaning the programmer control register, memory address, and CPU operation manually. The give very high efficient, but it's still time consuming to write and type to specific hardware platform. You would use assembly in situation where timing and performing are critical, such as embedded system or device driver. The third generation is where programming become much more human-friendly. These are high-level language most people start with, such as C, C++, Java, and Python. They're allowing the programmer to write instruction using English like keywords and structured logic, making the program easier and understand maintain. These languages are also portable, meaning the same code can often run the different system with minimal change. The trade-off is that compile interpreter has extra word to translate this instruction into machine code so they don't run fast as low-level language. The fourth generation moved even further from the hardware and focus on what the programmer want to achieve rather than listing step-by-step instruction. These languages are often found in specialized area, for example, SQL of database query, and MATLAB and scientific computing or R statistics analysis. The goal of four generation language is productive. You write a small amount of code and the system handle all the low level detail automatic. They are extremely efficient for their insane tasks, but they're usually not suited for building entire operation system or performing critical software. The fifth generation represent a shift toward language that deal with logic, constraints, intelligence, problem solving, instead of telling the computer how to solve the problem. The programmer define the rules and the system figure out the solution. These languages are commonly used artificial intelligence research, expert system, and natural language processing. All well example would be Prolog. They are powerful for reasoning-based tasks, but they are not commonly used for everyday software development and can be complex to work with. Moving into the part 3, I begin by look into the Python implementation. Python is a high-level program language, and it is a big strength is how easy it is read and write. Instead of worrying about the register memory address or hardware detail, Python lets us focus directly on the logic of the program. It handles things like memory management, data type, input and output, automatic in the background. In the calculator task, this makes a huge difference. The entire program can be written in just a small number of lines, and the code stays very clean and simple. Python also provides a built-in function for the reading user input, performing arithmetic and display output, with speed up development dramatically because Python uses an interpreter. The program runs through a visual machine instead of taking directly to the CPU. So execution isn't fast as lower level code, but for most everyday application, the speed is more than enough. Overall, Python represents a modern trend in programming, prioritize ease of use, fast development, and readability. Is the ideal for prototyping, education, automation, script, and general application development. The trade-off that Python cannot match the raw speed or hardware level control offered by assembly, which become more obvious once we compare the two implementations. Next, I will move to the assembly implementations. Unlike the Python, assembly work extremely close to the hardware. Every instruction directly control the CPU, from moving data into register to performing arithmetic and jumping between instructions. Because of this low-level nature, the assembly version of calculator is much longer and more complex. I have to manually manage things like register memory locations, branch logic, and input-output routine. Even simple tasks like adding two numbers or printing a result require multiple instructions. Writing assembly is lower, more technical, and much easier to make mistakes in. However, the benefits is that the final program runs very efficient. There is no interpreter, no abstraction layer, and no unnecessary overhead. The CPU executes exactly what we write, making assembly ideal for performance critical or hardware specific application. After completing both versions, the difference between Python and assembly become very clear. Python is far more conventions for writing program quickly. This code is shorter, easier and understand, and much more flexible. It's perfect for rapid development, testing idea, and creating application where raw speed isn't the top priority. Assembly is opposite. It takes much longer to development, and every detail must be handled manually, but in return, it provides maximum efficiency, minimal memory usage, and complete control over how the CPU operates. So overall, Python prioritizes productive and readability, while assembly prioritizes performance and control. The best choice depends on the goal of the project. For the challenge task, I extend the comparison by building a two-way traffic light system in both Python and assembly. A single button press start, then full sequence, where the rod A, rod B alternative choose blue, yellow, and red phase in the time cycle. I using blue color to replace the traffic light green light. In Python, implementation is straightforward. The GPIO library makes it easier to control the LED and read the button input, and the timing can be handled with simple sleep function. The entire sequence is readable and quick to implement. In assembly, the same logic requires much more detailed work. I have to manually configure the GPIO pin, manage delay truths, precise timing loops, and handling input at the register level. While the final behavior is identical, the assembly version is significantly more complex to write, but also given tight control over timing and hardware interaction. This challenge clearly shows how the Python simplifies development while assembly provides a full low-level control. Before the demo video for the challenge, I do a bit description for this. My left-hand side is rod A showing blue and right hand side is rod B showing red on the first phase. For the second phase, rod A turn yellow and rod B still on red for first 3 seconds. Then third phase, rod A change to red and rod B turn blue to go. While phase 4 again, the rod B changed orange, rod ready to stop for 3 seconds. Last phase, it turned back to rod A go and rod B stop. Now let's watch the demo video.